Hi everyone. In this video, we are going to study about the necessary condition for a real number to be between the two roots of a quadratic equation. For example, if we have a quadratic equation like this, ax squared plus bx plus c equals 0, and then we are going to find out what would be that necessary condition so that one of the roots, which is alpha, would be less than a real number k and beta will be greater than that real number k. That means the real number k will be in between alpha and beta. So graphically, if we look at it, in the first diagram, we can say, well, k must be inside the parabola somewhere in this red zone, somewhere in this red zone, anywhere. K can be anywhere in this red zone right here. If we don't include the roots, of course, we can exclude the actual roots. So let me do a hollow circle there maybe. So excluding the roots, then k can be anywhere in that red zone, as you can see in the first diagram. I have already created two separate videos where we studied the necessary conditions for both roots to be less than a real number or greater than a real number. Now this is the third video of that series, and here we are studying the necessary condition for k to be in between the two roots of a quadratic equation. Now here the condition is very easy. If k has to be inside the parabola, right? If k has to be inside the parabola, then what would be the value of f of k? If we take k to be anywhere, maybe let's say this is k right here, I'm doing a yellow dot on the red line there. And then what would be the value of f of k? Well, it will be a negative value when leading coefficient is positive. For this particular graph or for this particular parabola, f of k will be negative and f of k will be somewhere right here. So that is actually f of k. If this is our k comma 0, that's the point, the yellow dot on the x-axis inside the parabola, then f of k is obviously going to be negative. So here, when the leading coefficient is positive, for k to be in between the two roots, f of k is going to be negative. And similarly, let's take a look at the next set of diagrams where we have leading coefficient is negative, and there let's see what will happen to the value of f of k. So in the next set of diagram, again, this is our red zone right here. So k can be anywhere in this zone, in this red portion right here inside the parabola on the x-axis. K can be anywhere. So if we again take k, say suppose this is our k right here, I'm doing a yellow dot, and let's say this is our k comma 0, that point. And then what is the value of f of k? Well, f of k will be somewhere up there, right there on the graph. So this is our f of k right here. And if you think about it, when the leading coefficient is negative, f of k is actually positive. In the previous diagram, we saw that when the leading coefficient is positive, meaning the parabola opens upwards, f of k was becoming negative as long as k is in between the two roots. Similarly, when the leading coefficient is negative and the parabola is opening downwards, and if k is in between the two roots, then f of k is positive. So here we see a common pattern that we can say, hey, they are always having the opposite sign, meaning the leading coefficient and f of k, they have the opposite sign all the time. Whether leading coefficient is positive and f of k is negative, or leading coefficient is negative and in that case f of k is positive. So they are of the opposite sign. That means their product will be negative, and that is our necessary condition. So let me quickly make a note right here that their product, which is a times f of k, this is going to be negative. And that is the only necessary and sufficient condition to make sure that the real number k will be in between the two roots of a quadratic equation. We really don't need any other condition. This is good enough. This one condition will always guarantee that the real number k is between the two roots of the quadratic equation. Let me make a note of the same thing up here. So here I'll make a quick note. So this is the only condition, that a times f of k will have to be less than 0. This product has to be negative. Then only we can ensure that k is between the two roots of the quadratic equation. Now let's take an example. In fact, I'm going to use the same example that I have used in my previous two videos on this series. So let's take the same example here. So in our example, we have the quadratic equation as x squared plus p minus 5 times x minus 5 times p equals 0. That's our quadratic equation. And here we have to find out for what values of p, first root will be less than positive 3 and the second root will be greater than positive 3. That means positive 3 as the real number will be in between the two roots of this quadratic equation. So we have to necessarily find out the range of values of p for which number 3, positive 3, will be in between the two roots of this quadratic equation. And to solve this kind of problem, we are just going to use the only necessary condition, which is a times f of k has to be negative. That's the only necessary condition here. Now what is k in this case? Well, this is actually k, that positive 3, that is actually the k, right? And what is a? A is the leading coefficient. In this example, the coefficient of x squared term is just 1, so the leading coefficient is positive 1. So then from here what can we say? Well, a is 1, so 1 times f of k means k is actually positive 3 here, so f of positive 3, this product must be less than 0. And from here let's calculate f of 3, because 1 times f of 3 is same as f of 3, right? So f of 3 would be 3 squared. So we are going to substitute the value of x as 3, so 3 squared plus p minus 5 times 3 minus 5 times p. This is our f of 3. From the given quadratic equation we can say, well, then f of x, we can assume that f of x is actually equal to x squared plus p minus 5 times x minus 5 times p, just the quadratic expression that should be considered as the function of x. So here then f of 3 would be 3 squared plus p minus 5 times 3 minus 5 times p, right? So this has to be less than 0. Now if we solve a little further, so this is actually 9 plus 3 times p minus 5 times 3, that is 15, so that's negative 15, and then we have minus 5 times p, and this has to be less than 0. And if we solve it a little further, what do we get? We get 9 and minus 15, so that would be negative 6. And then we have positive 3 times p and negative 5 times p, so that would be negative 2 times p. All of that is less than 0. And if we divide both sides by negative 2, then what will happen? Then we are going to get a positive 3 and a positive p, and of course the inequality sign will flip, so this will be greater than 0. And from here we can say, well, then definitely p must be greater than negative 3. You keep the p on the left hand side and transpose 3 onto the right hand side. So that is our final solution set here. And that was the only necessary condition for positive 3 to be in between the two roots of this quadratic equation. And if we want to write it in the interval notation, then we can say therefore p must be in this range right here, so greater than negative 3, that means from negative 3 up to positive infinity. Now if we want to quickly validate this solution set, we can maybe try a value of p. So from this range, maybe we can take a value of p as maybe 0 or 1. 0 will be the easiest one. Maybe we can try with 0. So let's try with 0, the value of p at 0, and let's see if it satisfies our condition. Positive 3 has to be between the two roots, right? So if we use 0 for the value of p, because that 0 will be definitely in the range of negative 3 to positive infinity, in that range 0 is a real number. So now we are going to test with p equals 0. And when p equals 0, what would be our quadratic equation? Well, our quadratic equation was originally like this. It is x squared plus p minus 5 times x and minus 5 times p is equal to 0. Now if we use 0 for the value of p, then from here we can say, well, let's use 0 wherever we see p, we are going to put 0 there. So this will be x squared plus 0 minus 5 times x minus 5 times 0, that is equal to 0. And from here what do we get? We get x squared, then minus 5 times x and minus 0. I'm not going to write the 0. So all of this is equal to 0. And if we take x as a common factor, then we have x times x minus 5. All of that is equal to 0. And then from here we can say that x is equal to 0 or x minus 5 is equal to 0. And from here we can say, well, then definitely x is equal to 0 or positive 5. So now we have found the two roots of this quadratic equation, 0 and positive 5, right? And now if you think about it, is the positive 3, the real number positive 3, in between the two roots? Yes, of course it is in between the two roots, because if the two roots are 0 and positive 5, then definitely positive 3 is in between 0 and 5, and that's exactly what we wanted to verify. So looks like our solution set is working for positive 3 to be in between the two roots of this quadratic equation, which is x squared plus p minus 5 times x minus 5 times p equals 0. For positive number 3 to be between the two roots of this quadratic equation, the possible range of values of p can be in this range from negative 3 to positive infinity. Of course, excluding the negative 3, because p has to be strictly greater than negative 3. I hope everything made sense. Thank you for watching. See you in the next video.